Okay guys, welcome to just a little video that I'm making going through all of the example problems for the Module 1 slides. So let's go ahead and start with number 1. I already have the little path drawn out. So to find the displacement, I'm just going to write that as DIS for displacement. Or actually I'm going to do distance first, so DIST. And to do that, I'm just going to count every square. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So then we have 31, and we know it's meters. And distance doesn't need a direction. So that's all we need to do. For displacement, actually, I'm going to write that as delta x for displacement. That's our x final minus our x initial, and we're just going to count the squares in between since it's a straight line. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can say 9 meters, and there's a couple of ways we can say that. We can say 9 meters in the positive x direction. We can say 9 meters I hat, and we can say 9 meters east slash right. All of these would be acceptable. Okay, for number 2, I'm not going to go through and count again, just because I think that you guys can do that if you need to. So the distance for this is 17 meters, and our delta x for this one, we are going to have to use the Pythagorean theorem to find, oh god, I actually wanted this, to find, this distance right here. So we know that this is a right triangle because this is a right angle right here, and this has a side length of 1, 2, 3, and this has a side length of 14. So we know that this delta x equals the square root of 3 squared plus 14 squared all under the square root. Delta x equals 16.64 meters northeast, or delta x equals 14 I hat plus 3 j hat. This is a vector. This is a vector. Okay, for number 3, we have that the distance, again, we are just going to count up all of the squares. That is going, but for here we have, again, a right triangle that we are going to need to find our hypotenuse of. And for this case, we have 1, 2, 3, 4 plus 1, 2, 3, 4. And so this is the square root of 4 squared plus 4 squared. And counting these all up, if you put this in your calculator, you get 17.66 meters. I forgot my units here. Meters. Oops. Okay, or you could say delta x equals 1.41 because you would do this hypotenuse, square root of 2, 1.41 meters northeast, or delta x equals I hat plus j hat. Okay, and that's it for the distance versus displacement examples. So now number 4, for our average velocity and acceleration, we have an object travels at a constant velocity 100 meters in 250 seconds. So we know that our displacement is 100 meters and our time is 250 seconds. The way I know this is displacement and not distance is that it's a constant velocity. There is no acceleration, so we are not changing direction. This is 100 meters in a straight line. So we know that V, and I'm going to go ahead and say V average just so that we can keep this correct, is delta X over T. Time is always changing. You can't add the delta T. You don't have to, which is 100 meters over 250 seconds, which is going to give us 0.4 meters per second. We know that our acceleration is equal to delta V over T, where this is equal to VF minus V naught over T equals 0.4 meters per second minus 0.4 meters per second all over 250 seconds, and this equals 0 meters per second squared. Just ran out of room. Okay, for problem 5, we have the same delta X, the same T, but here we also have an initial velocity of 0, so it's at rest, and a final velocity of 0.8 meters per second. I forgot to add my little caret there. Okay, so we know V average is equal to delta X over T, and this is the same exact thing. 100 meters over 250 seconds is going to give us 0.4 meters per second. But now we have our acceleration, and that's going to be delta V over T, which is our VF minus V naught, so 0.8 meters per second minus 0 meters per second all over 250 seconds. If you put this into your calculator, we're going to get 0.0032 meters per second squared. This seconds per squared because we have our seconds here and our second here. Second per second over second is per second squared. Okay, problem number 6. Oops. Okay. Problem number 6, we know that it has a velocity of 20 meters per second, I hat, and time is 10 seconds. We want to find delta X. Well, we know that V average is equal to delta X over T. This implies, doing some algebra, that delta X is equal to V average T, which in our case is equal to 20 meters per second I hat times 10 seconds. Our seconds are going to cancel out. This implies that our delta X is equal to 200 meters I hat. Okay, so now we're going to go to our kinematic equations. I already have explained 7, so I'm going to go ahead and skip that one. But, oops, I said I was going to skip it right as I was writing it. For number 8, we have a car starts from rest and then accelerates constantly to a velocity of 20 meters per second in the positive x direction in 30 seconds. So our known values are going to be BF is equal to 20 meters per second. V naught is equal to 0 meters per second. T is equal to 30 seconds. Okay, so we are going to use the equations VF equals V naught plus AT add all of my little carets there. These are vectors. And delta x equals v naught t plus 1/2 a t squared. Okay, now we can get to solving this. For this first one, vf equals v naught plus a t. This implies that a is equal to vf minus v naught over t. Oh my god, this is our equation that we already had for acceleration. Comes straight from the kinematic equations. Okay, anyways, this implies acceleration. I am so bad about putting my little carets on, so please, if in class you notice that I'm forgetting my carets, let me know. Okay, so our acceleration is equal to 20. I'm actually going to write this bigger so that it's visible. Acceleration is equal to 20 meters per second. This is I hat minus 0 meters per second. 0 doesn't need a direction. Over 30 seconds. And this implies that acceleration is equal to 0.667 meters per second squared. Okay, and then we need to find our displacement. And there are different ways that you guys can do this. So if you did a different way than me, that's fine. It's kind of like a puzzle, and you're just trying to see what pieces you can find to fit together. Doesn't necessarily matter what order you put the puzzle in, just as long as you have all the right pieces in the right order. Okay, and this equals, well, we know that v naught is a 0, so I'm going to go ahead and cross that out. 1/2 0.667 meters per second squared times 30 seconds squared. This squared is going to go onto that seconds, which is going to cancel that out. And this is going to equal 300 meters. Okay. Problem 9. A car has a velocity of 30 meters per second in the positive x direction, then accelerates constantly to a velocity of 20 meters per second in the positive x direction in 5 seconds. So yes, it does say accelerate, and the velocity is getting lower. Acceleration can be positive or negative. In this case, our acceleration is going to be negative because we are going slower in the same direction. So a car has a velocity of 30 meters per second. I had to 20 meters per second. I had t equals 5 seconds. And these are going to be the same equations that we did up here. So I'm going to zoom out so I can see them as I write, just for time's sake. V naught plus a t delta x equals v naught t plus 1/2 a t squared. Okay, I'm being a little sloppy with this just because I'm talking while I'm doing it. I will also upload a picture of my work, and that will be a little bit more clear, I think. Okay, so for this one, we already have done our algebra to find our acceleration, and we know this from our acceleration from above. So this is 20 meters per second I hat minus 30 meters per second I hat all over 5 seconds. And this is going to equal negative 2 meters per second squared I hat. So this is negative I hat. It's going in the negative x direction. Our velocity vector is going this way, whereas our acceleration vector is going this way. But our velocity vector is still going in this positive direction, even though our acceleration is in the opposite direction. Okay, and then delta x equals v naught t plus 1/2 a t squared equals, our v naught is not 0 this time, so we cannot cancel it out. Oh my god! 30 meters per second times 5 seconds, that's going to cancel out. Plus 1/2 times negative 2 meters per second squared. I hat. This is also I hat. Times 5 seconds squared. Boom, 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 boom. This is going to be negative. So delta x is equal to, if you put this all in your calculator, 125 meters. We are still going in the positive x direction, so our displacement should still be positive. This is all tracking. Okay, so now problem 10. Oh my god, my computer is frozen. Okay. A car has a velocity of 30 meters per second in the positive x direction. The driver of the car sees a deer in the road 50 meters ahead. The maximum negative acceleration of the car is negative 10 meters per second squared. What is the maximum reaction time they have to stop the car? Okay, so for this one, I am going to, again, write down my knowns. And I know that v naught equals 30 meters per second. And I'm going to go ahead and really quick rewrite this, but I find it easier to write with this thinner one, so I'm going to go ahead and do that. And hopefully it'll help with viewing, and you can still see it. 30 meters per second. Also, my pencil kind of skips sometimes, so I'm sorry if you're seeing some weirdness there. Our VF is going to be 0 because we're needing our car to stop. Our delta x, and I'm going to label this as delta x deer because we're going to have a couple of different delta x's, you will see in a minute, is going to be 50 meters. And our acceleration is equal to negative 10 meters per second squared. Since we want the maximum reaction time, we want the maximum acceleration as well. Okay, and then for our equations. So I know that in order to figure out this problem, I need to find, well, reaction time. I'm not going to be able to find the reaction time just from this because I need to know how long you have traveling at this velocity in order to stop in time for this. So what I need to do is I need to find the distance that the car can go before it can stop and then find the time it takes to travel that distance. So for this, whoa, I was going to write out the whole word, but I'm not going to do that actually. I know that for the equations, I'm going to need a delta x, I have a VF, I have a V naught, I have an A. So this is VF squared equals V naught squared plus 2A delta x. And then I know that my delta x reaction time is equal to my delta x deer minus, and this is going to be delta x acceleration. This is the delta x that goes with our acceleration, so that's why I'm calling it that. It's the one where we're applying our acceleration to. So VF squared equals V naught squared plus 2A delta x acceleration. I know that 0 squared meters per second squared is equal to 30 meters per second squared plus 2 times negative 10 meters per second squared delta x. So then I have 0 is equal to 900 meters squared per second squared minus 20 meters per second squared. Delta x implies that I'm just going to go ahead and say that we're adding 20 meters per second squared delta x to both sides. That would cancel out with that, and then divide over. So that implies that delta x equals 45, and I kind of forgot to carry over my little a there. Oops. 45 meters. Our meters are going to cancel out. Per second squared, per second squared. Pretend these are on the other side. This meter will cancel out with that while I'm dividing them. Okay, so then I know my delta x reaction is equal to 50 meters minus 45 meters. It's equal to 5 meters. Okay, and in this 5 meters of reaction time, you are traveling at a constant velocity, so you can use your easy velocity, constant velocity equation. We know that velocity, I'm going to say average, is equal to delta x over t. This implies that t equals, sorry that my pencil is skipping, delta x over v average. So t is equal to 5 meters over, what was our 30 meters per second. Boom, boom. This per second is going to flip up. This is equal to 0.167 seconds. That's your reaction time. So sometimes you guys have to be a little bit creative in finding this. You can't just go straight to finding the time. You have to do a couple of different equations first. Okay, so I think that is it for our kinematics, and we're going to go into free fall. So an object is dropped from a cliff 100 meters high. What is the object's velocity just before it hits the ground, and how long does it take for the object to hit the ground? Here are my knowns. Delta y, this is vertical, so I'm going to be using y and j hat instead of x and I hat, just to keep it accurate. 100 meters, and I'm not going to include our direction vectors. I haven't been in the past couple of ones, so sorry about that without saying anything, but I just haven't been for, just to keep this video brief. Okay, so our acceleration, which is only acceleration due to gravity, we know that is negative 9.8 meters per second squared, and our v naught, since it is dropped, it is starting at 0 meters per second. It's not thrown down, it is just dropped down, free fall. So for this, I know that bf squared equals v naught squared plus 2a delta x, because I am trying to find our vf, and I have v naught, I have acceleration, and I have delta x. So this implies that bf equals the square root of, this is 0, 2 times, I am not going to include the negative sign in this because our negative sign is going to create an imaginary number under this square root sign, and we do not want to deal with complex numbers for this. Our velocity final is not going to be a complex number. It is going to be a real number, and the negative sign is only telling us direction. So we will know that this is a negative velocity, but we do not need to include the negative in our root. So where was I? Oh yes, and delta y is 100 meters. These meters are going to be meters squared, and so that's going to be perfect. This equals 44.267 meters per second. This does not look like a 44. Okay, and then we also want the time it takes. So for this, we're going to do our handy dandy VF equals V naught plus A T. This is my favorite kinematic equation. I don't know why, it just is. And I'm not going to rearrange this one, I'm just going to leave it as is. Our V naught is 0. And so that gives us, actually, I am going to rearrange it. T is equal to VF over A. equal to, and we know this is going to be negative, so I'll just go ahead and add that just for funsies. Okay. Our VF is 44.267 meters per second over negative 9.8 meters per second squared. Our seconds squareds are going to cancel out, and our meters are going to cancel out, so this is going to be seconds. That's the correct one. Our VF, this is going to be negative. This is negative. These negatives will cancel. And that's also j hat. This is going to give us 4.5 seconds. Okay, 412. For our knowns, this time we do have a initial velocity. So I do not want to write in purple right now. Our V naught is going to be 5 meters per second. Our VF is going to be 0 meters per second. And why is VF 0 meters per second? Because I'm going to do this in halves. I'm going to draw a little diagram. So say I have the ball here and I throw it up. Before it comes back down, it needs to stop. It's going to be up here with a V equal to 0, because as it's coming up, it can't instantaneously change directions. It needs to wait for a second up there before it can come back down. So for a split second, the ball is completely still before it comes down. That is why my VF is 0, and then you'll just need to remember to multiply it by 2, because I am asking for the entire time it takes to reach its initial position, and this is just the time it takes to reach the top. And of course, our acceleration is negative 9.8 meters per second squared. Okay, also, since our acceleration is the same on the way up as it is on the way down, our velocity is going to be changing at the same rate, so our time is going to take the same amount of time to reach the top than it is to reach the bottom. That's going to be the same length path. Okay, so for this, I'm going to use VF equals V naught plus a t. This says that 0 meters per second equals 5 meters per second plus negative 9.8 meters per second squared t. Doing all of our algebra, which is just subtracting this over and then dividing, this implies that t is equal to 0.51 seconds. Okay, now that we have that, I'm going to do both legs of the journey. That is for it to reach the top. For it to come back down, we're going to do 0.51 seconds times 2, which is 1.025 seconds for the entire journey. Okay, then our delta x is equal to V naught t plus 1/2 at squared. And this, we are going to do how high up it goes, right? So how long does it take for the ball to reach its initial position? So the time is how long it takes to reach its initial position, but we want to know how high it goes, not the entire distance it travels. We want the displacement. So our V naught is going to be, okay, 5 meters per second times 0.51 seconds plus 1/2 times negative 9.8 meters per second squared times 0.51 seconds squared. These seconds squared are going to cancel out, and these seconds cancel out. And this is going to say that delta x is equal to, and I actually don't have this one written down. Oops. Plus 0.5 times negative 9.8 times 0.51 squared is, oh, I totally do have this one written down, I'm sorry, 1.276. I don't know why I thought I didn't have it. That's my bad. But yeah, that is how high our ball gets. Okay, so now we're on to our graphing problems. So problem 13, we have, what is the slope of the function from t equals 0 to t equals 10 seconds? So it's going to be easiest for you to be looking at this alongside of the video because I don't have the images, and I do apologize for that. But we know that slope, or m, is equal to the change in y over the change in x. So the change in y in this case is going to be, we start from 0 and we end up at 60. Over our change in x, we start from 0 and we end up at 10. So negative 60 over negative 10 is going to be a positive 6. Now for our velocity, we know our average velocity is a change in x over a change in t. This is looking very similar. Our change in position, well, that's on the y-axis. So it's going to be 0 minus 60 over our change in time, that's on the x-axis. So it's going to be 0 minus 10 equals a positive 6 meters per second. And I totally forgot my units. Sorry about that. So as we can see here, our slope and our average velocity are exactly the same. If you want to do this for any portion of the graph, you are going to see that the slope is always going to equal the average velocity of that section, which is really cool. For our velocity versus time graph, that is going to be question 14. We have recall that slope is the rate of change of a function, or the change in y over the change of x. So we have our slope is the rate of change in y over change in x. What is the slope of the function from t equals 12 to t equals 14? From t equals 12, we have our y is 2, and at t equals 14, our y is negative 6. This is going to equal 8 over negative 2, which equals negative 4. Now our acceleration, we have our change in v over our change in t. Our change in velocity, well, our velocity is on the y-axis. So it's going to be 2 meters per second minus a negative 6 meters per second all over our change in time, which is still 12 seconds minus 14 seconds. Technically, final should be minus initial, so I am doing this backwards, but it is still going to work out since I am doing it the same way each time. I just have a habit of doing that. So again, this is 8 over negative 2, meters per second, and that's going to be negative 4 meters per second squared, per second squared. And so as you can see, that the slope of our velocity versus time graph is going to be our acceleration. Pretty awesome. Okay, very last one. Thanks for sticking with me. For number 15, we have our acceleration versus time graph. So This one is just a series of three horizontal lines. Which time segment is the object speeding up? So as you saw in our problem 10, our acceleration was negative because we were slowing down. Our acceleration was in the opposite direction of our motion. So when our acceleration is negative, we're going to be slowing down. Our acceleration is negative here at 4 is less than or equal. Whoa, what happened? Is less than or equal to t less than or equal to 6. You could also write this in interval notation between 4 and 6. That kind of makes more sense to do. In which, oh, I'm doing this backwards. So slowing down is this one. I read the questions in the wrong order. In which time segment is the object speeding up? Well, that's just the opposite. That is when our acceleration is positive. It's in the same direction as motion. So that is between t equals 0 and t equals 2. And I am a little rusty at my interval notation. These are inclusive. And in which time segment is the object experiencing constant velocity? Well, when velocity is constant, our acceleration is equal to 0, and that is going to be between seconds 2 and 4. And that covers all of it. So thanks for watching my Module 1 video. I hope this helps you guys, and if you still have any questions, please don't hesitate to go ahead and email me, and I will do my very best to assist you